Hello and very good day. My name is Asrani and I'm with the Department of Electrical and Electronic Engineering, University Malaysia, Sarawak, UNIMAS. And the focus of my presentation is about the decentralized peer-to-peer electricity trading simulation dashboard. So basically, this is the roadmap of my presentation, which basically consists of five main parts, which are introduction, system architectures, methodologies, P2P electricity, trading simulation, and we'll end up with conclusion. Without further ado, first I would like to begin this presentation with introductions. With the rise of the distributed energy resources or DER, such as rooftop solars and PV system, as well as the electric vehicles, it reshaping the modern electricity distributions. Therefore, the traditional top-down power delivery is progressively evolving toward the prosumer-centric models. In addition, P2P energy tradings enable users to buy and sell electricity directly within the localized networks. So this increasing the renewable energy utilizations and reducing the dependency of the centralized utilities. The real-world deployments, such as the Brooklyn microgrid projects and emerging blockchain-enabled platforms, highlighting the growing adoption of the community-driven energy models. So the P2P electricity market contributes to the grid resilient, cost saving, and carbon reduction, especially when integrated with EV, energy solar systems, and home energy management system. So the next presentation is on the system architectures that has been carried out in these works. So the proposed system models of the small residential community with four types of participants, which are solar homes, EV homes, hybrid solar EV homes, and normal residents. So these figures illustrate the conceptual models of the P2P residential energy networks. The P2P electricity models, as illustrated, allow the households to trade electricity directly with one to another's, and this therefore fostering a decentralized and localized the energy sharing system. So in these models, participants can generate electricity using the renewable energy sources such as solar panels to store the excess energy in batteries and therefore trade a surplus of power with neighbors or other within the networks. The next presentation is on the methodology that has been carried out in these works. So the solar generation is modeled using a sinusoidal irradiance profile, which is approximates the typical clear sky PV productions with the midday peaks, where T is the hour of the day, which is from the range of 0 to 23, and PV is the installed PV capacities. EV charging demand is a model with higher activity during the evening hours. So these are reflecting a common user behaviors, and the normal residential demand is represented as stochastic process with bound derived from typical household consumptions. The P2P matching mechanisms is implemented using a simplified supply-demand balancing models, and all trades are recorded with timestamp. The seller buyers identifiers, the traded volume, the monetary cost, which are forming a transaction logs, which is suitable for further analysis or later integration with blockchain-based settlements. Now, let's look into the P2P electricity trading simulations. So this is the simulation settings and the parameterizations, which involve the simulation step, base, grid price, and solar capacity. These figures illustrate the solar duration in time series, and it visualizes a hourly solar generation using a cyclic irradiance-driven generation curve that emulates the typical tropical solar behavior like Malaysia and Philippines. And the waveform display the low output during the early mornings, rapid rise toward the noons, and symmetrical decline in the evenings. So the battery state of charge, or SOCs, plots demonstrate the chargings during surplus periods and discharging during peak demand hours. This emphasizing the role of storage in energy balancing, and this figure illustrate the hourly state of charge of the community battery over 24-hour simulation period of the proposed P2P electric systems. As can be observed, the hourly state of charge of the community batteries showing the charging during the midday surplus and discharging during the evening peak in the P2P electricity system. So this figure illustrates the EV and the resident demand of the simulations. Uh, there are two distinct load profiles that are represented. First is the EV charging demand, and secondly is the conventional residential consumptions. The EV demand curve demonstrates the intermittent high load blocks that correspond to charging session typically initiate during the morning departures and midday top-up chargings or evening return to home charging cycles. So these sessions shows a significantly higher power requirement compared to the normal household appliances. So next is the figure that shows that P2P trading activities of the simulated scenarios. So this dashboard compute the successful peer-to-peer energy trades per hours based on the availabilities of the surplus solar energies and the presence of the local demand from the EV as well as the residential load profiles. So this metric is visualized as a time series bar charts that highlight the intensity and the frequency of the P2P market interactions. So in conclusions, so this book presents a lightweight interactive simulation dashboard for P2P trading activities, which is developed using by the Python frameworks. So the system models the energy generations, the demand patterns, the dynamic pricings, and matching algorithms in order to emulate the residential P2P microgrids. The prosumer and consumer are represented with distinct profiles, which including solar homes, EV homes, hybrid solar EV home, and the traditional conventional consumers that allowing the visualization of the energy flow and market activities. This dashboard, in addition, provide real-time charts, automatic trading logs, and the simplify market clearing mechanisms. So this making it suitable for teachings, prototype, and also for community microgrid feasibility studies. The results demonstrate that the capability of the simulation models, the household interaction, and the visualize the trade behavior across the daily cycles. Future work will extend the current framework by integrating battery storage system or BSS dynamics, enabling the analysis of energy arbitrage, self-consumption optimization, and support the grid service. In addition, the incorporation of block-based transaction ledgers will enhance the transparency, traceability, and trust in P2P market operations. And finally, coupling the dashboard with the real-world IoT sensors from smart meter, for instance, and also the renewable energy system can improve the realism of the simulation and, of course, pave the way toward the real-time monitoring and decision support application for community scale microgrids. So these are the main reference for this research. So these are the rest of it. So with that, thank you for listening.